we're going to talk about linear regression today. This is from chapter 8, sections 1 and 2. So our goal is to find a linear equation to model the relationship between two numeric variables. We call them x and y. And x is what we would normally call the independent variable. It's the one that is, if we graph it, it's on the horizontal. And we can also call it explanatory or a predictor variable. And then y is the dependent variable. It's the one that would be on the vertical axis if we are graphing this with a scatter chart. It also is called the response variable. The things that we're going to cover from section 8.1 and 8.2 are creating a scatter chart of the explanatory and response variable, measuring the strength of the correlation between the x and y variables with the correlation coefficient. It's important to know that R, the correlation coefficient, only measures the strength of a linear correlation. We will also find the linear equation that relates x and y. When we create that equation, we use y hat because it is a statistic and we want to separate that out from the true value of y. So we put that hat on there to recognize that we're actually estimating the mean value that y takes on. And it's equal to some value that's an intercept plus the slope times x, an inputted explanatory variable. Then we'll also calculate something called residuals, right? We will take the predicted value and find the difference from the actual data value for a given value of x. And then we'll create a scatter chart of those residuals and x. Also, we'll calculate something called the coefficient of determination, which is just the correlation coefficient r squared, and that has a particular meaning. And then finally, we're going to use the linear equation that we come up with to predict a mean value of y for a given value of x. So we'll start talking about an example. And this data that we're going to look at is in the Google Sheet that is available to you on Canvas. We're going to run through these notes, just pulling out the values from the spreadsheet and plugging them in, and then check out the other video that goes through how you use the Google Sheets to calculate the different values. So we have an example about long jumpers, and we want to know the relationship between a long jumper's best jumping distance, we're calling that y, the response variable, and their average takeoff error, we're calling that x, the explanatory variable. And then what kind of pattern do the points show? Another way to say that is how does the jump distance change as average takeoff error gets longer? Another way to say that is a long jumper's best jumping distance correlated to their average takeoff error? All right, so if we check out the data, we've got 13 different athletes. For each of them, we have a value for the average takeoff error, the x value, and we have a best jumping distance, the y value. And then in the scatter chart, each of those athletes is represented by a point. So if we identify a particular point, let's just say this one right here. If we look at the list and figure out which one this corresponds to, this looks like it is athlete number 12 with average takeoff error of 0.07 centimeters and best jumping distance of 5.2 meters. And each of those other points is going to correspond to a particular athlete. The scatter chart can't tell us anything definitive as to if we have linear correlation or not, but we can start to get a general idea if there is possibly linear correlation. And what we can see from this is it does look like as x values get larger, as x values go from the left to right, it does look like the y values, the best jumping distance, is increasing, even if it's ever so slightly. And that would indicate positive linear correlation. So there's another example in the spreadsheet on financial aid. I'm going to let you do that on your own, and I'll provide a key for that.